I'm Jake O'Neill, creator of Animagraphs, and over the last few months, I researched, scripted, 3D modeled, animated, and scored this project. This is how the Golden Gate Bridge works. The suspended structure spans 6,450 feet, or about 1.2 miles. 2/3 of which is the center span at 4,000 feet. Driving over the center span would put you at 265 feet elevation above the water, leaving 230 feet or so of clearance for ships passing beneath. Like my model of HMS Victory, for example, at 205 feet tall. The towering structure is held aloft by huge cables, formed in place at the site. A single cable with its proper rise and fall between towers comes to 7,650 feet long, or 1,200 feet longer than the total bridge span. Peering inside the cable, we see that it's actually made of 27,572 individual galvanized steel wires. Unraveled, that's enough small wire to make 13 trips coast to coast, or go 1.5 times around the equator. If we follow the cable to the tower top and take away its protective cover, we can see that wires are actually formed into groups called strands. There are 61 strands, with an average 452 wires per strand. The strands are cradled here in a highly engineered saddle. By the way, here at the tower top, we're about 750 feet above the water. That's as tall as a skyscraper with 50+ floors, or one Hoover Dam, to borrow the model from my recent project. Tracing the cable back toward the ground, we pass by more suspender cables that hold up the roadway. At the shoreline, the cable cuts through huge structures that underpin the approach roadway. Before diving down into the South Anchorage. Inside the anchorage, cable strands fan out from a splay collar to individual anchoring points that are embedded in massive concrete blocks which have been keyed directly into excavated bedrock beneath, and to each other. Because you can't simply whip up a climbing knot to tie off a 3-foot thick cable rope that weighs as much as the fully constructed Eiffel Tower at around 11,000 tons. The suspension bridge form is a timeless, ancient, elegant design with few support structures that block waterways. It can span unbelievable distances at great heights for tall ships to pass beneath, and do so without much, if any, disturbance to existing water traffic while under construction. That said, they're high-tech installations that take longer to build, require deep scientific knowledge to build well, and skilled ongoing maintenance for the life of the structure. Let's build this wondrous bridge, starting at the piers, which are the foundations for the 2 towers. One at the north, or Marin side of the bridge, and one at the south, San Francisco side. They're identical in many ways, but the South Pier is the more involved of the two because of its location. It sits 1,125 feet from the shore. With its lowest point at 100 feet below the water's surface. It's surrounded by an equally huge concrete fender to protect the pier from collision and the sheer force of the ocean itself. The San Francisco Bay is widely considered to be the world's largest landlocked harbor, meaning the most water area at about 435 square miles, with the smallest outlet, in this case a single narrow point about a mile wide, called the Golden Gate. Tides push and pull the mass of ocean water through this narrow point at an average 4 to 7.5 knots, which rounds to 5 to 9 miles per hour. As a truly mind-blowing comparison, apparently most well-known rivers like the Mississippi travel at something like 1 to 3 miles per hour as a very general average. So this point in the San Francisco Bay not only experiences the violence of the ocean at its surface, but also underwater flows more powerful than many huge rivers. To aid in building the South Pier, an access bridge or trestle is constructed from the shore to the pier site. It was originally made of flat-sided steel beams and took 8 months to build. At completion, a 2,000-ton steamship, lost in a dense fog, ran into the trestle about 400 feet from the shore. The structure was repaired, and then a storm that kicked up huge waves carried off the pier end, followed by another storm which wrecked all but 600 feet. Instead of steel, a new trestle was made from wood for more rapid construction to stay on schedule, with round supporting legs to better withstand crashing waves. At a height of 25 feet above the water instead of the original 5 feet. During trestle construction, excavation was also begun at the pier site by means of a barge with a derrick on deck. A derrick is a lifting device similar to a crane, but distinct with its main mast from which the lifting boom operates. It's a stiff-legged derrick in this case, with fixed supporting legs at mast sides. The standard excavation practice of using rock drills to make holes for dynamite wasn't possible 60+ feet below water. Instead, a new method was devised to excavate the extremely hard rock shelf. A guide pipe is placed through a tall timber frame extending from the barge deck. The frame helps keep things aligned as the barge pitches upon waves, sometimes as high as 8 feet. Metal legs keep the pipe clear of operations below. A 20-foot long, 5,000-pound shaft with a steel point is dropped onto the rock below, requiring multiple blows to chip a hole about 2 feet deep into the rock. Then a small 2-foot-long pointed explosive device is dropped down the pipe. The fuse will light on impact, giving an additional 60 seconds time before detonation, which allows time to hoist up the reusable part of the mechanism. 15 or so of these charges open up an 18-foot deep hole into the rock. To accept a much larger 8-inch diameter by 20-foot long explosive charge. The final charge is lowered into the hole and then hammered further into the rock by dropping a steel shaft upon it. Electric wires for firing are brought up by divers, and the barge is moved a distance away. 6 of these large explosives are set off at a time, and a dredging barge removes loose material. The original construction plan was to build the fender wall on a shallower, stepped foundation conforming to the natural slope of the site, and excavate only the pier area down to -100 elevation. One side of the fender would be left open to float in and submerge a reinforced metal enclosure called a caisson. This huge pressurized box allows construction to proceed deep underwater in a dry environment. For close inspection of the rock at this critical pier foundation site. Also, rock excavation and concrete pouring, since the caisson serves double duty as the actual concrete forms. There was some intense political and scientific doubt directed specifically at this foundation site, so means for thorough inspection were essential. To build the fender wall, a metal guide structure was submerged and anchored to the sea floor at the end of the access trestle. Concrete forms are slid down guide rails, stacked and riveted together. This tower will be one of 22 such vertical sections, concreted in blocks to form the fender wall. However, the same storms that carried away the original access trestle also wrecked this first guide rail and formwork. Plans were revised to excavate the entire area under the pier and fender to a level base at -100 elevation. It would be much easier to secure things in place on a level plane instead of a slope. The foundation was placed in successive blocks from the bottom up instead of one full-height tower at a time. All this to withstand the incredible ocean forces at the site that caused the previous failures. Divers do the precarious work of attaching forms to the ocean floor and to each other. Conditions are extreme. Visibility at depth was pretty much zero, so they had to feel their way around much of the time while wrangling these dangerous floating metal structures. The incredible currents at the site meant divers were safest working in the 20-minute gap between tides, 4 times a day. They were often forced to surface quickly. Rapid decompression can cause physical pain and injury to divers at a minimum. Concrete is placed through a watertight pipe called a tremie. Suspended from the derrick boom in this case, extending 100+ feet to forms below. A special concrete formulation is used that resists mixing with water. The pipe must be kept submerged in concrete at all times, such that fresh concrete displaces the outer protective shell as it rises. The tremie pipe is slowly lifted as the form fills, keeping fresh concrete sealed and maintaining its integrity as it cures far underwater. A pair of steam-powered derricks on tracks begin from the access trestle outward around the fender ring, lowering forms into place for each neighboring block. Divers guide these large metal forms into place and attach them. Fender construction continued as planned, with the eastern end left open at -40 elevation, and the remaining ring brought up to 15 feet above the water to accept the caisson. Excavating everything down to -100 elevation made the fender walls a lot taller in the end, requiring a wider base for proper support. The wider base would not fit the caisson, which had already been designed and fabricated. Plans were again revised. Instead of fitting the caisson to the ocean floor, the entire interior of the fender would be concreted up to -64 elevation. The dredging and excavation process up to now had given new insight into foundation rock conditions, so inspection wells at intervals were deemed sufficient for ongoing bedrock sampling. The pressurized caisson would sit atop this foundation block for integration into pier construction, similar to the original plans. The caisson was towed to the site and delicately slipped into the fender interior. However, waves kicked up through the night, and the caisson pitched violently, damaging itself and threatening to cause catastrophic damage to the fender wall as well. It was towed out under duress to open ocean and sunk as refuse. Under a final plan revision, the entire interior area of the fender was concreted up to -35 feet below sea level, and all ocean water pumped out for construction of the actual tower pier. Inspection wells with pressurization chambers allowed inspectors to descend and inspect foundation rock, resolving doubts about the suitability of the site. The inspection wells were also then filled with concrete. Here is the completed fender compared to an American football field and an office building. It's really big. The pier structure was concreted inside the fender. With embedded metal frames and steel tabs that protrude above the pier surface for anchoring to the tower above. Once complete, ocean water is allowed to fill the channel between the fender and pier for some additional mass and added strength, with pipes for water to flow in and out. The north pier form is similar to the south without the fender or underlying foundation block. A cofferdam is built with thick timbers and filled with rubble, so that ocean water can be pumped out of the site during construction. Returning to the south side, let's zoom out for a second and take in the tower that is to be placed upon this pier. It extends 720 or so feet above the pier surface. The tower's steel alone will weigh 44.5 million pounds and bear most of the suspended structure, including the roadway and cables, for an additional 123 million pounds resting on this tower. To perform under these Herculean demands, the pier surface must be meticulously prepared. A large grinding wheel and traveling frame pass over the concrete area under each tower leg, grinding the surface to a flatness within 1/32nd of an inch. A paste is applied and 5-inch thick steel plates are set in this paste for a resulting flatness within 3/1000ths of an inch. To secure these base plates, large metal dowels, 4.5 feet long by 6 inches in diameter, pass through holes in the plates into the pier beneath, and are set into place with a thin cement mixture called grout. The embedded pier frames are pre-stressed using powerful jacks to stretch the frame upwards. The jacks will be released after these tabs are permanently riveted to the tower above, pulling the tower legs into a very tight, seamless fit with the base plates. Now, tower construction can begin. Near the pier, we see a section of tower steel awaiting placement. It's made from steel panels about 7/8 inch thick, riveted together at the corners. The unit is designed for ideal shipping and handling, since tower steel sections like this one are prefabricated in Pennsylvania and shipped through the Panama Canal to California. I've set a few of these units in their proper place at the base of the tower. From the top down, you can see the internal web of 3.5-foot square cells. This kind of cellular construction is not only convenient for fabrication and transportation, it's also incredibly strong for its weight. It's flexible and accessible inside for repairs and inspection throughout. Sections are staggered vertically where possible for added strength. To lift these sections into place, a steel frame is installed between the tower legs with a pair of stiff-legged derricks at its sides. This machine is called a traveler. Some tower sections have pre-cut slots for steel plungers that extend from the traveler frame. As construction progresses upwards, the traveler can lift itself up to the next set of holes, extend its plungers, and anchor itself into place for work around that level. The holes are 35 feet apart vertically, and there were about 15 lifts in total before the traveler reached the very top of the tower. Scaffolds advance with tower construction. Coal-burning forges on the scaffolds heat rivets to red-hot temperatures. They're quickly passed to workers through a system of pressurized air tubes and valves. Once received, a worker with an air-powered rivet hammer deforms the red-hot metal into place for a permanent connection. A worker at the other side supports the force of hammering with a metal brace. There are pre-cut holes throughout the structure to accommodate supply lines for rivet passing tubes, air-powered tools, and so on. Internal cells and outer panels are all riveted together on site for a total count of 600,000 plus rivets on this tower alone. There are manholes, ladders, and access ports throughout the entire tower interior. Some openings are screened to make a floor. The mind-bending labyrinth has no less than 23 miles of ladders. A 26-page manual was produced for navigating the ladder maze. The cells decrease in number from the base. There are 2 huge steel cross braces above the base which connect the towers beneath the eventual roadway elevation. Zooming out a little more, we see 4 trusses between the road level and the tower top. Tower cells decrease around each truss. If I reveal the exterior steel paneling, you can see familiar design elements that cover cells as the tower gets thinner near the top. There are access doors and ladders at each truss. And also internal access. There's a small service elevator in the center that goes all the way to the top. The completed tower is a sight to behold. The north or Marinside Tower was actually constructed first, with the South San Francisco Tower following after. With towers completed, the cable spinning process can begin. The 7,500 foot long, 11,000 ton continuous steel cable ropes will have to be constructed on site, one thread at a time. There's simply no better way to transport or place such a thing over the tops of these 2 sky-high towers. It's called cable spinning because the cable is literally woven on site. Though the cables are huge, the process requires constant attention to minute details along the entire cable span. To provide that kind of access, footbridges must first be installed about 3 feet below the cable path from end to end. A cable is hoisted to the tower top by derrick and attached to a couple of sheaves above the saddle. The loop is then used to haul up 1.5-inch thick steel cables, with stops pre-installed that fit into an adjustment block. A similar block sits in a steel frame at the Anchorage, which is tied down with more cables and metal into concrete. The center span has similar components between towers. To install the first cable here for hauling up other cables, a barge towed the line across the bay from tower to tower where a derrick raised it up. This is the only time ship traffic had to be stopped completely during the construction process. Wooden footbridge sections are prefabricated and slid up supporting ropes in trains of 10 at a time, to be properly fastened in place at the tower top first, moving downwards. This happens at both sides and both anchorages simultaneously to maintain balance. For the center span, sections are hoisted to tower tops and slid down into place. Where the footbridge is steep, There are raised boards every so often for added traction in climbing. There's also a motorized rope at one side to act as an escalator, where workers can take hold for help with the arduous climb. This climb is no joke. Much of the side span rises at about a 27-degree angle from flat. With road grades, a 45-degree angle, or rise equal to run, comes out to 100% grade. That means this side span holds about a 51% grade for more than a quarter mile. That's considered steep even for experienced hikers, and might require a hiker to scramble, using both hands and feet together, depending on the trail. Every 10 sections, there's a special portion of walk built on a metal frame as a fire break. Planks can be quickly torn off and cast away to separate the burning area. Spacing between planks allows wind to pass through for less swaying in blustery conditions. There are metal crosswalk trusses at quarter points for moving between spans. At the middle of the center span, there's a built-up truss and a small suspended coordination office, which comes into play during spinning. Brackets run along the walk to carry many communication lines and other electrical wires. There's a wire mesh covering the central gap. Sections can be removed for access beneath the footbridges down to the eventual roadway. A robust network of storm cables runs under the footbridges, with strategic anchoring and lines to hold things in place through the wild weather systems often experienced at the site. A system of lights marks these cables for traffic moving through the bay. As we've already seen, accidents with huge passing ships are a very real concern. With a full span platform in place to work from, cable spinning can begin in earnest. An accurate but simplified spinning setup looks like this. Wire from a reel is attached to a bracket called a strand shoe. You'll understand the name in a minute. It goes behind the shoe and up over a pulley on a motorized carriage. As the carriage starts to move, you can see we're pulling out a loop of wire. If I paint some stripes on this loop, you can see that one side naturally lays still as the loop is unreeled. While the other side moves a lot. This side is the dead wire. And the moving side is the live wire. That's why we use a pulley here, so the wire can freely slide through as the loop gets bigger. Once at the other side, the wire loop is removed and wrapped around the opposite shoe. To get the job done, we want to make a lot more loops. However, because of where our reel is located, we can't pull out another loop unless the carriage goes all the way back to the other side empty, wasting a trip. To make things most efficient, there are reels here at the far side as well. if we add another pulley to the back side of the carriage, we can pull out a new loop from the far side. I'll make them different colors for easier viewing. This is a pretty good spinning setup. These little wire loops will make our thick bridge cable in no time. Once this set of strand shoes fills up, the bunch of wire loops is banded together and set aside, while we fill a new set of shoes. The banded collection of wire loops is called a strand, hence the name strand shoe. Once we've woven many strands, the entire group is squashed together and wrapped for the final cable. By the time the Golden Gate Bridge was under construction, crews had become very good at spinning cables for suspension bridges. The final arrangement has enough pulleys to carry 3 loops at a time from each side. Carriages go halfway and back again. Workers swap all 6 loops at the midpoint so they can finish their journey. With that simplified model in mind, let's head to the South Anchorage and start spinning our actual bridge cable. The first wire loop is about to be unreeled. Here is our itty-bitty wire, at just 2/3 the thickness of a pencil. We see the strand shoe nearby. Right now, the shoe is held by a beefed-up metal arm called the strand leg, leaving an open side for wrapping loops. The wire comes from a very heavy reel. These are shipped in and replaced by derrick when empty. Wire passes from the reel through a special counterweight pulley and eventually to the strand shoe. It has a counterweight because the reel is actually motorized and is controlled by a worker who watches the counterweight to adjust unreeling speed and thus keep the wire at the right tension. A wire too tight or too loose means parts either won't move freely or wire could slip free as it's being spun. The wire is secured at the shoe and looped around a carriage pulley like we saw before. The carriage is firmly attached to its own cable, which is driven by an electrical motor and spool atop the anchorage. Like the motorized reel, the carriage drive cable has a counterweight to monitor slack as the carriage travels. Let's send our carriage on its journey. The carriage moves at a max rate of about 7.4 miles per hour or 650 feet per minute. As the carriage travels over the footbridge, we see rollers bolted to the surface. Remember from before, one side of our wire loop lays still, while the live side moves a lot. These wheels support the moving live side of our loop. As the carriage continues, you'll notice a pipe and cables above the walkway. The pipe has a bracket and split pulleys or sheaves. The moving carriage and its drive cable are supported as they pass through the split sheaves. These carriage support pipes are placed at about 200-foot intervals. As we near the top of the South Tower, we can see there's a lot going on here. We'll keep mostly focused on our single wire loop for now. The carriage passes through another set of split sheaves as it travels over the tower. Remember, this one loop will eventually be part of a strand, and the strands a cable. That cable will permanently reside in the tower saddle. Until then, while the strand is being spun up, our wire is held in its own special channel off to the side, called the strand saddle. The dead wire lays here, while the live wire rolls upon sets of wheels at the side. Keeping everything meticulously organized is essential. The carriage crosses over the tower and begins its descent to the midspan point. Here, at the midspan station, we see another carriage approaching from the other side. Loops will swap carriages here at the midpoint to continue their journey to the other side, just like our simplified model from before. At this point, I should tell you, there are actually 8 spinning carriages on 4 motorized loops split between our 2 main bridge cables. Don't worry though, this is the only time I'm going to be showing them all at once like this. Since the carriages are fixed to their drive cables, they're positioned so that one carriage is at the anchorage, while the other is at the center span. One drive loop covers half the bridge. The whole loop actually goes all the way to the opposite tower top before turning around to keep added hanging weight off the midspan with all the support drive machinery I haven't shown here. They're not usually all in use at one time, but this way, there's always a working carriage available, even if the others are stopped for repairs, and so on. You can begin to imagine what it must take to keep organized and safe, with tiny webs of wire loop slinging back and forth over miles of bridge span, in all kinds of weather. There would be multiple carriages running, and remember, one carriage can carry 3 loops of wire at once. The midspan office stays in constant communication with towers and anchorages, so teams at all points work together. Let's rejoin our loop as its journey ends. A loop of wire makes its full trip from end to end in about 15 minutes, including travel and transfer time. At the other side, it's removed from the carriage and looped around the opposite strand shoe. As you can see, the North Anchorage here has its own reels and spinning setup like the south side. So loops are unreeled each from their respective anchorage as they're wrapped around opposing strand shoes, just like our earlier demo. With so many loops going at once, there are reels stacked all over the place, with wires and pulleys everywhere you look. Now, our new loop of wire can be adjusted for proper sag. Even though it's just one tiny thread in the scheme of things, every single loop is dialed in with great precision. Spans are adjusted individually by clamping the wire at the tower saddle and attaching a hand-powered winch called a come-along to add or remove slack. I've shown a greatly exaggerated version here to get the point across. Let's head back to the South Anchorage and see how things are taking shape there. When a reel runs out, the wire must be joined to a new reel. A separate tool deforms wire ends into an oval shape with slanting ridges. The ends are inserted into a sleeve and pressed together. Thousands of strength tests were performed to arrive at this particular connection design and method. This wire has to hold strong. Back at the Strand shoe, you can see I've advanced our timeline some to where the shoe has been completely filled with loops after many, many carriage trips. This strand is complete. Workers open the strand at intervals to make sure each individual wire of about 452 total wires follows the proper sag angle within the strand. Wires out of conformity are cut and spliced to be brought into proper alignment. Tape is wrapped around the strand at intervals. The strand leg upon which the strand shoe is temporarily held for spinning is designed to move. It has a 150-ton hydraulic jack to pull the very heavy strand and shoe back into its final position. Once aligned, it's enclosed between a pair of steel brackets and permanently pinned into place. The brackets at the sides are called eye-bars. We're going to fill all of these eye-bars with strands, so the reels, carriages, platforms, jacks, and everything else has to move with each new strand. Tracing components backwards reveals another linkage to more eye-bars set in concrete. If we remove the concrete, you can see the eye-bars serve as a chain back to a retaining rack. At the strand shoe, you'll notice it has a slot at the center for spacers or shims that would change final shoe placement. That's because, once complete, the strand itself has to be checked for alignment and its sag adjusted. It can be allowed to slide over tower tops or clamped to adjust sag at center or side spans, as shims are placed in the shoe to finalize its position. Strand adjustment is so important that crews would adjust a strand during the day and again at night. This very long bunch of steel wires can expand or contract a lot, being exposed to ever-changing weather, direct hot sunlight, cold nights, and more. Since strand adjustment needs proper patience and time, our multi-carriage setup allows spinning to happen on the other cable in the meantime. Spinning and adjusting crews trade sides between processes. As we head back to the tower top, you'll remember our strand sits in a separate channel for spinning. Now that it's complete, it needs to be lowered down into its final place in the main cable saddle. Even though the finished cable will appear so sturdy and indestructible, this individual strand requires delicate care to avoid flat spots, sharp kinks or bends, or otherwise deforming in any way from its own rounded profile and the pre-calculated curvature of the saddle. With a closer look, you can see the saddle curve isn't a simple symmetrical slope from its apex, but rather a very specific curve to fit different cable sag angles from side to center span. For lifting the strand, there's a device suspended above the channel called a balance beam. It has adjustable turnbuckles along its spine, with slots to hold thin metal straps. The straps are placed under the strand as it forms, because it would be impossible to do once the very heavy strand is complete. These straps are now inserted into and gripped by the turnbuckle bracket, which closes the strap as it's tightened. Two hydraulic jacks delicately lift the strand, which now weighs around 250,000 pounds, while supporting and keeping its predefined curve, and carefully deposit the strand into the cable saddle. There are actually 4 strand saddles in this working area, and all might be in use at once as multiple strands spin up together. The split pulleys for passing carriages can shift to align with particular strand saddles. Let's take a moment to look at the main cable saddle. It was manufactured and machined in sections because it's too big to make in one piece. The precision machining happens inside the saddle arc, where surfaces are shaped and polished to hold strands in a specific orientation as they sweep gently over the saddle curve. If I add a cutaway of all finished strands in the final cable, you can see the intended hexagonal cross-section. The final cable outside will be round, but inside the saddles, this is its permanent shape. This tilted hexagon, with its sharp angles pointed downward and corresponding saddle grooves at each strand, is intended to help the cable resist flattening or slumping under load. Engineers learned from previous bridges where cables were laid with the flat side of the hexagon facing down, causing measurable flattening of the final cable with all weight placed upon it. Flattening changes cable dimensions, alignment of attached parts, and may also affect its strength over time in this critical area. Getting this right is so crucial that even individual strands might have more or less wires within to get the desired outcome as they all squish together under load. Exact wire counts are kept for each strand while spinning because they're not always the same depending on the strand's location in the cable. Incredible. The thin straps used to lift each strand remain permanently stuck in place beneath the heavy strand, but are trimmed as short as possible. Let's head down the side span again toward the South Anchorage. I'm showing a handful of completed strands here, resting in cable formers. Formers are placed at intervals. These are metal retainers to hold strands in position, but also keep some space between them for good air circulation, and therefore more even expansion and contraction throughout the strand group as the cable comes together. Nearing the anchorage, we see the steel truss that supports the footbridge and spinning carriages. There are miniature strand saddles here too, with a simpler balance beam to move a recently completed strand from the spinning position into the cable area. With that, you've seen the entire spinning process. Carriages make literally thousands of trips back and forth, unreeling thin wire loops and filling up shoes until all 61 strands are complete, anchored, adjusted, and hoisted into position inside the cable. During spinning, formers hold strands in a hexagon pattern like the saddle. Now that spinning is complete, strands will be compacted into a circle to make the final cable. The goal is to reduce spaces or voids between strands as much as possible, so that in the end, all of these thousands of tiny wires will act together as one very strong cable mass, uniformly sharing the extreme stresses placed upon the cable, no matter the location of any single wire or strand within. A compacting machine is assembled in halves. It rides upon a supporting sled. A ring of 12 hydraulic jacks with curved feet surrounds the bunch of strands. Each will exert 81 tons of force, for a total of 972 tons, as all jacks act together to squeeze the strands into shape. There are some added components for cinching metal bands around the compacted cable to hold everything tightly in place. Workers move the compactor about 3 feet using hand winches to compact a fresh section of cable. The compactor can do 3 moves. Before the entire sled must be advanced and anchored for another round of compacting. The sled rides smoothly upon contoured wooden wheels, front and back. With an angled wooden work surface, planks at the front to the footbridge, and stairs at the back. 6 compacting machines were in use throughout the installation at various starting points. A single machine can compact about 204 feet of cable in an 8-hour span. The cable will eventually also be wrapped in a continuous wire sleeve for its ultimate exterior treatment, but not yet. With the cable compacted, it can now begin to receive the load it's meant to carry. And that will cause movements that make it ideal to apply final wrapping after the cable has settled to its ultimate shape, with everything suspended. Let's look at a few more cable details before we suspend anything from it. Back at the South Anchorage, we arrive at the footbridge truss and strand saddle we saw before. The splay collar will be bolted together here to secure the splay point. That is, the point from which all strands branch out to their individual cable shoes. Each strand has an additional sleeve before its cable shoe loop. Each cable shoe and eye-bar chain has its own ideal angle from the splay point all the way back to the retaining rack. The rack and much of the eye-bar chain is embedded in a massive block of concrete. Another solid mass of concrete will be placed atop the anchorage to more permanently hold things down. These blocks are stepped or keyed together to resist movement. The foundation block is also keyed with excavated bedrock beneath. All of this exacting, surgical level detail is what it takes to permanently secure cables of this size and magnitude. Let's have a look around the anchorage while we're here. The finished anchorage has thick concrete walls for protection. Trusses sit on the anchorage roof for the approaching roadway. Nearby concrete support towers, or pylons, have openings for cables to pass through. During construction, footbridges and spinning equipment also pass through this tower. There's a mini steel-framed arch bridge here over an American Civil War-era fort that was built to defend the bay entrance, and was left in place at bridge construction as a part of San Francisco's history. Cables run diagonally through the arch, crossing another pylon. The Marin anchorage mirrors the south side internally, but with different exterior styling. The complete unwrapped cables are ready to take on suspended weight. In preparation for hanging the roadway beneath, suspender cables are installed at 50-foot intervals along the length of each cable. Suspender cables are held by cable bands with sleeves for each suspender. The heavy band is bolted to the main cable in halves. The suspenders must hang straight down at each location. So, every single band has to be custom made based on its relation and angle with the main bridge cable. Bands at the center are level, while bands near the towers hold a steep angle while keeping suspenders pointed straight down. It becomes more obvious why suspension bridges are expensive to build, requiring many specific custom parts on a massive scale. There are 250 of these bands in total, with a pair of suspender cables each. Far below, the roadway steel begins to take shape, starting at the tower. All of these pieces are heavy, hulking bits of steelwork in their own right, hoisted up and riveted together by skilled steelworkers. The framework is attached to and thereby hung from suspender cables. Steam-powered traveler derricks, weighing 79 tons apiece, use a 75-foot boom to manipulate parts. They creep along the developing roadway, moving in opposite directions from both sides of both towers to maintain balance in the system. A moving safety net hangs below the working edge. While another temporary net is strung beneath the entire length of roadway as trusses are completed. As the travelers move back away from the center, they place finishing steelwork for sidewalks, beams, or stringers beneath the actual road surface, lamps, and more. Concrete for the road surface and sidewalks is then placed. The road lanes are poured in sections 20 feet wide by 50 foot long with expansion joints in between. There are some interesting things going on where our new hanging road and tower meet. Remember, the tower has been designed with a pre-calculated amount of flexibility, so it can move or sway some with changing conditions. And of course, our suspended road will be constantly moving as well. To accommodate movement between the tower and roadway while keeping the system within its designed limits, the roadway truss has a braced steel pin that rides in a slot which is connected through beams and trusses to the tower. There are ramped bump stops on steel beams that can make contact to gradually exert a damping force as the truss pulls away from the tower. At the road surface, there's an expansion joint, with sets of interlocking metal fingers at each side for safe passage over the fluctuating gap. The roadway truss also rests upon giant rocker arms underneath, affixed at tower sides. with multiple stories of ladders and platforms for maintenance access. At the sidewalk, there's a covered section of handrail that telescopes between moving sections, since the roadway sidewalk and tower sidewalk are actually two separate structures. The original transition was a step, but I found better examples of the updated ramp design, so I've used that instead. The approach span has a similar setup and behavior, but smaller, to accommodate less movement and less component weight. Let's rewind a bit for a little demonstration to make sense of a few remaining components. As load is placed upon the cables, with roadwork, frames, concrete, and so on, the much longer center span will naturally take on a lot more weight than side spans. The resulting pull toward the heavier center span could cause towers to unnaturally bend inward from their intended vertical alignment at rest. Cables would also be pulled out of alignment, negatively affecting predefined sag angles throughout the system. Let's see how these forces are accounted for as the roadway comes together. We'll head to the cable saddles at the top of the tower. In its current position, with no roadway trusses suspended from the cable below, the saddle is set back 5 feet 6 inches from what will be its final centered position above the tower. It sits on a bed of rollers, with a pair of hydraulic jacks and heavy bracing at the front and back. As more and more weight is suspended from cables, jacks move the saddle on its rollers. Gradually adjusting this support point means towers remain vertical and don't bow inwards. And cables keep their pre-planned sag angles from side to center spans as they take on more weight. When the last road truss is suspended, the saddles will have reached their final centered position at the tower top. The saddle is permanently bolted to the tower. Its rollers are filled with cement grout to set them in place. And the jacks and supporting framework are removed. Let's head down to the south pylon, where the hanging road meets the grounded approach road. The detailed and extensive calculations mean that roadway sections should align at this point in the process. However, if for any reason they do not, there's a set of components inside the pylon tower here to make adjustments. This is called the cable tie-down. A metal rack holds a row of jacks, with cable ropes and bracing secured around the main bridge cable. The jacks press downward, opening up a gap where spacers or shims can be inserted. for a permanent adjustment at this location on the main cable. Which of course also affects everything hanging from it, including the placement of the road deck as it meets the unsuspended approach road. Also in this compartment, there's a large steel rocker arm to support hanging roadway trusses while allowing some movement. With the roadway in place and cables set to their final adjustment, the cables are ready for their protective, weatherproof wrapping. A wrapping machine is assembled in parts around the cable. A large bobbin is loaded with wire from a reel. It has an electric motor and drive gear. The bobbin dispenses wire at opposing sides as it spins around the cable. Plungers with L-shaped brackets are lowered to ride against the freshly laid wire. Which keeps windings tight, and also helps advance the machine with each new coil as it wraps around the cable. Cable bands are already permanently placed, so the machine is designed to operate on bare cable or on already wrapped cable for ease in maneuvering around the bands. It must be disassembled to pass over bands to the next unwrapped section. There's a rolling frame above to support the machine during these operations. As with other components, the wire is treated or painted with various compounds for resilience against the elements. With cables wrapped, the bridge is complete. For normal folks like you and I, it can be difficult to register how organic this steelwork giant really is. The roadway is actually suspended in air, hanging freely from those big metal ropes, held aloft over the ocean by flexible towers. Let's look at some built-in design limits to drive the point home. Say the center span somehow fills to capacity while side spans are empty. At the same time, the temperature has risen to a sweltering 105 degrees Fahrenheit, a full 40 degrees over the 65-degree mean temperature which was used to calculate average conditions at the site. Steel in the roadway and cables expands when hot. Add to that the heavy, uneven load, and the middle of the center span has dropped to its maximum designed 10.8 feet of downward deflection. Reverse these conditions, with temperatures having plunged to 25 degrees Fahrenheit, now 40 degrees below the designed average. All bridge steel shrinks when cold. This shrinking, combined with the unevenly filled side spans, means the empty center span has risen 5.8 feet upwards. So the total possible deflection here at the center is 16.6 vertical feet. Sure, you're not likely to see it happen instantly. However, it's not that unbelievable to imagine the bridge moving a lot during the course of just one day. During these movements, towers are allowed to bend up to 22 inches shoreward, or 18 inches toward the center, for a total deflection range of 40 inches, or about 3 1/3 feet. To really push all the limits, let's look at wind pressure. In an absolute gale force, 120 mph wind, the center span can sway an incredible 54.5 feet, or 27.7 feet to either side. The bridge itself is 90 feet wide, so that range is over half of its width. Again, these are maximum limits, rarely to be seen. However, if you're suspending a permanent 6-lane highway hundreds of feet in the air in an exceedingly fickle climate system above an angry ocean, to stand against all the elements both day and night, year after year, you can expect Mother Nature to surprise you. In 1951, a sustained 60 mph wind caused notable damage throughout the structure. Additional stiffening steelwork was added under the entire roadway span as a result. Another addition in the 1950s is a motorized scaffold system to make maintenance easier. There are suspended, multi-story enclosed scaffolds at the sides that move together. And separate scaffolds that run along tracks atop stiffening trusses underneath the roadway. These will have been altered recently for further modern additions. There are access doors at the sidewalk level, daunting ladders and stairways tacked to tower sides atop connecting trusses, and a catwalk along the finalized top of the tower with other components. The saddles are capped with weather-tight steel panels. There are warning beacons at the very top for air traffic. As we fall back to take in the whole bridge, I'd like to mention that this project faced intense scientific and political hurdles to the very end, with holdups, delays, and miles of red tape to navigate. It's always been really hard to get anything done and done well when you're dealing with an entire country, and the past isn't all that different, actually. The Golden Gate Bridge is truly an Art Deco masterpiece, where form meets function, where dramatic, unimaginable design requirements drive the resulting appearance. She can only stand by the exertion of the highest skill in engineering, design, construction labor, and maintenance. And I love that.